Hello students, last time we have seen how Einstein's quantum theory of light explains the various features of the photoelectric effect. According to Einstein, light is made up of particles which are known as the photons with energy E is equal to some h nu, where nu is the frequency of the incident radiation, and momentum P is equal to h by lambda, where lambda is the wavelength of the incident radiation. And by using this quantum theory of light, and we have seen how he beautifully explains all the features of the photoelectric effect which have been observed experimentally. Now today we will summarize some important properties of the photon. Now number one, a photon always travels at a speed c is equal to, which is denoted by the c, is equal to 3 into 10 raised to power minus 8 meters per second in vacuum. The velocity of the light, in other words, we can say this photon of light, when it is traveling in vacuum, it is traveling approximately with the speed of light which is equal to 3 into 10 raised to power 8 meters per second. This is the property first of the photon. Now, property second, the speed of the photon is independent of frame of reference. If we look at the photon, its speed is independent of the frame of reference. If the observer, whether it is at rest or whether it is in moving. So related to both of these observers, the velocity of the photon is always, that comes out to be c. That is, it is independent of frame of reference. And third property, that is the rest mass of photon is zero. जो rest mass जो photon का है, that is zero. What does this mean? It means photons doesn't exist at rest. Photons जो होते हैं वो exist नहीं करते हैं rest पर. This is a property number third. Now, if we know that it is actually, as per the Einstein, a photon is a packet of energy. It is a packet of energy. And at the same time, there is a mass energy equivalence. If we relate the energy of the photon with the mass, m is equal to mc square is equal to E. mc square is equal to E. This is the equivalence between energy and the mass. Now, since as I told you in the property number third, photons doesn't exist at rest. In other words, we can say the rest mass of photon is equal to zero. Now, effective mass of the photon, we can determine the effective mass. If this packet of energy, if this photon, whose energy as per the Einstein is given by h nu, if it wire a mass in this universe, then what will be the effective? What is the mass of the photon if it exists in the form of matter? That is known as the effective mass of photon. That effective mass of photon is given by, that is determined from the mass energy equivalence. That is m is equal to E divided by c square. From this relation, m is equal to E, this c square goes in the denominator, and the relation is this. M is equal to E by c square, or which is equal to, as per the Einstein, energy of the photon is equal to h nu, where nu is the frequency and h is Planck's constant. H nu by c square, which comes out to be h by c lambda. That is, m is inversely proportional to the wavelength of the incident light. इसका मतलब क्या है? इसका मतलब है, for example, if we take photons of red light or if we take photons of blue light, both, तो as जितना लैम्डा ज्यादा होगा उतना मास कम. Since if we take the red photon and photon of the red light, we can say the mass of the photons of the red light will be less as compared to the mass of the photons of the blue light. Why? Because the wavelength of the red light is greater than the wavelength of the blue light. So this is the effective mass if we talk of in terms of the mass. Similarly, property number 5, that is each photon has definite energy and definite linear momentum. जो आइंस्टाइन ने दिया था उसी वक्त जब उसने प्रपोज की थी क्वांटम थ्योरी ऑफ लाइट, ही सेज each it is a packet of energy is equal to h nu and momentum p, because momentum is a property of a particle. He relates the particle property with the wave property, that is lambda, and that lambda, and that momentum is equal to h by lambda. वही है यहां पर फिफ्थ प्रॉपर्टी में, each photon has a definite energy and definite linear momentum. Now property number 6, let E and P be the energy and linear momentum of a photon of light, and nu and lambda be the frequency and wavelength of the same light when it behaves as a wave. अगर हम मानते हैं, अगर हम डिनोट करते हैं एनर्जी ऑफ ए फोटॉन एंड मोमेंटम, एनर्जी ऑफ ए फोटॉन if we denote that by E and momentum of the photon by P, तो अब जो फोटॉन ऑफ पर्टिकुलर लाइट का जो है, तो अगर उस लाइट जो हम लेते हैं, अगर उसकी फ्रीक्वेंसी है न्यू एंड उसकी वेवलेंथ है लैम्डा, जबकि ये बिहेव करते हैं एज अ वेव, जब इसका बिहेवियर होता है एज अ वेव, तब दिस एनर्जी E is equal to h nu which is equal to hc by lambda after substituting the value of frequency, and momentum is equal to h by lambda which is equal to E by c, where h जो है it is a fundamental constant, you know that is Planck's constant, and its value is 6.626 into 10 raised to the power minus 34 joule second. Thus from this, if you look at these relations, this relation, this and this relation, here h is a fundamental constant and c is also a fundamental constant, both are fundamental constant. So from this, energy is inversely proportional to the wavelength of the light used, and similarly here momentum, here h is fundamental constant, we can say momentum of a photon is inversely proportional to the wavelength of the light used. Thus all photons of light of particular wavelength lambda have the same energy, because here energy depends upon the wavelength of the light used, because h and c are constants, so we can say E is inversely proportional to the wavelength. That is, the energy, if we take the photons of a particular wavelength, that all those photons have the same energy and all those photons have the same wavelength, as is clear from the relation, whatever the intensity of radiation may be. कोई भी इंटेंसिटी आप रखिए, whatever be the intensity, by increasing the intensity or by decreasing the intensity, it means we are decreasing the number of photons crossing per unit area per unit time. This is the intensity variation, how intensity affects on the number of photons. It affects the number of photons crossing the unit area in unit time, but it will not, by changing the intensity of the radiation, it will not change the energy of the photon, nor it changes the momentum of the photon. Now, property number 7, photons are electrically neutral. जो photon जो होता है यह electrically neutral होता है. In other words, we can show it is not deflected by the electric and magnetic field. That is, it is not. You have already studied that the charged particles which are electrically charged, they are deflected by the electric as well as the magnetic field. But चूंकि जो photon जो होता है, it is electrically neutral, that is why it is not deflected by electric and magnetic fields. Property 8. In a photon particle interaction, when a photon interacts with the particle, during this interaction, the total energy and the total linear momentum of the photon remains conserved. It remains conserved during this collision. Energy as well as the momentum. However, the number of photons, they may increase or decrease. The photon may be completely absorbed, or a photon of part of its energy may be absorbed by the, for example, when it collides with the electron, part of the energy of this photon is absorbed and the rest part may be emitted as a new photon of lesser energy. Thus we can say the number of photons during the collision, it may increase or it may decrease. Then that is, number of photons are not conserved, but during the collision of the photon with the matter, the energy as well as the momentum of the photon remains conserved. Both are these were some important properties of the photon. However, the number of photons in the collision. When the photon interacts with a matter, like if it collides with an electron, then both its energy as well as linear momentum remain conserved during the collision of the whole system, I mean to say. However, the number of photons may not be conserved in the collision. It may increase or it may decrease. So these were some important properties of the photon. Thus, now dual nature of radiation. Now dual nature of radiation. Now you have seen how this, in this chapter you have studied the photoelectric effect and its experimental features. You have summarized them as laws of photoelectric effect, and you have seen how Einstein explains these different features of photoelectric effect on the basis of the particle nature of light. In the previous chapter in wave optics, you have studied the large number of phenomena like reflection of light, refraction of light, interference of light, or diffraction of light, all these phenomena, reflection of light, refraction of light, interference of light, or diffraction of light, all these phenomena have been explained by taking light as a wave. In other words, we can say these phenomena has been explained on the basis of wave theory of light. At that time, light behaves as a wave. But there are other phenomena, as you have studied in this chapter, that is photoelectric effect. Photoelectric effect. Photoelectric effect, and we have summarized the different laws of photoelectric effect, experimental features of the photoelectric effect, and we have seen these experimental features, what we have observed experimentally, these have not been explained by taking light as a wave. But then Einstein proposed a particle theory of light. He takes the photon picture, and we have seen how beautifully he explains the all features of light. Thus, it was concluded that it is the experiment. It was concluded that light sometimes behaves as a wave or sometimes it behaves as a particle. But at a particular instant of time, it is either a wave or a particle. We can't say it is wave as well as particle, but at a particular instant, it is either a wave, you have to take it as a wave nature, or you have to take it as a particle nature. And from this, we have seen that it is the experiment which decides the nature of the light. If we take the Young's double slit experiment, or if we take this diffraction of light, these phenomena can be explained. This interference of light, or diffraction of light, or refraction of light, these can be explained when we take light as a wave. That means in these phenomena, in these experiments, like in double slit experiment, light, in these phenomena, light manifests its wave nature. Or if we take, on the other hand, if we take photoelectric effect, light manifests its particle nature. Thus, it was concluded that light has a dual character. Sometimes it behaves as a wave, or some other times it behaves as a particle. On the basis of that, on these experimental facts, what we have observed and their explanation, on the basis of this, it was concluded that light has a dual nature. Sometimes these phenomena can be explained on the basis of the wave nature of light. Wave nature of light. And this is explained. There are some other phenomena like Compton effect, that too is explained when we take light as a particle, like photon picture, as a photon picture. So this was about the dual nature of radiation. Now we do some numericals related to the photoelectric effect. The example first. Example first. In an experiment on photoelectric emission. Now, example first. In an experiment on photoelectric emission, following observations were made. Wavelength of the incident light is equal to 1.98 into 10 raised power minus 7 meter. And second, stopping potential is equal to 2.5 volt. Find part A, maximum kinetic energy of the photoelectrons. Part B, you have to calculate the work function. And part C, you have to determine the threshold frequency. Now, solution. First of all, we have to determine the maximum kinetic energy. We know that how maximum kinetic energy is related with the stopping potential, because first of all, you will see what are the parameters which are given. The given parameters are lambda is equal to 1.98 into 10 raised power minus 7 meter, and stopping potential V naught is equal to 2.5 volt. Now we have to calculate the maximum kinetic energy, K max. We have to calculate work function phi naught, you have to calculate it, and threshold frequency. These are the parameters which we have to calculate. The given parameters are the wavelength of the light and the stopping potential. We know that K max, how maximum kinetic energy is related to the stopping potential. This is equal to E into V naught. This is the relation. Maximum kinetic energy, that is equal to charge of the electron and the stopping potential. Or K max is equal to E, V naught is 2.5 volt into E into and volt, 2.5 volt. This is equal to E into 2.5 volt, or we can write it as it is 2.5 electron volt. Thus, the maximum kinetic energy of the photoelectrons when a photosensitive material is illuminated with a light of wavelength this, the maximum kinetic energy that can have that is 2.5 electron volts. This was the part first. Now part second. Now work function. You have to determine the work function. Now, what is the energy of the incident photon is given by E is equal to h nu, or which is equal to hc by lambda. Since both h and c are constants and lambda is given, so therefore you can determine the energy of the incident photon. So which is equal to, you will substitute the corresponding value. You should remember, in terms of electron volt, this h into c, it is equal to 12400. Electron volt. In angstroms. This is the value of AC. 12400 electron volt angstrom divided by wavelength 1.98 into 10 raised power minus 7 meter. So since we have write down this h into c in angstroms, we will write down this also in angstroms, so that angstrom and extra will get cancelled and we will get the answer. Energy of the photon, incident photon in electron volts. What is the energy of the electrons in electron? This photon is in electron volts, or we can write it as 12400 electron volts angstrom divided by, this can be written as, when we convert it in angstroms, angstrom means 10 raised to power minus 10. That means you have to both divide 10 raised to power minus 3 and multiply by 10 raised to power minus 3. You will get 1980 angstroms. 1980 angstroms. This, when we calculate this, it comes out to be 12400 electron volt divided by 1980. Or now we know the relation how the energy of the photon is related with the maximum kinetic energy and the work function. That is, E is equal to, as per the conservation of energy, that is K max plus work function, or work function can be written as E minus K max, maximum kinetic energy, or this E is equal to 12400 divided by 1980 electron volt. We keep this in electron volt because we have determined the K max in electron volts, minus 2.5 electron volt, or this is equal to, after solving this, you will get 3.76 electron volt. You will get the final answer. This is how you can calculate the work function. Now part C. Part C is, you have to calculate the threshold frequency. You know that work function is equal to Planck's constant times the threshold frequency. Implies that nu naught threshold frequency is equal to phi naught divided by h, or this is equal to, phi naught. We have determined 3.76 electron volt divided by h. H is 6.62 into 10 raised to power minus 34 joule second. Now we'll convert this, or this is equal to 3.76 into electron volt means 1.6 into 10 raised to power minus 19 coulomb volt. That is joule. 6.62 into 10 raised to power minus 34 joule second. This is joule, and joule will cancel. After calculating, you will get, it is 9.1 into 10 raised to power 14 hertz per second is hertz. Now example 2, a metallic surface is irradiated with monochromatic light of variable wavelength above a wavelength of 5000 angstrom. That means this is the threshold wavelength, 500 angstrom. No photoelectrons are emitted from the metal. When a metallic surface is irradiated with a light whose wavelength is greater than this, more than 5000 angstroms, so no photoelectron emission takes place. It means when we keep the wavelength of the order of 5000 photoelectrons are just emitted. If we keep the wavelength of the incident radiation above this, no photoelectric emission takes place. That means this is the threshold wavelength. When an unknown wavelength stopping with an unknown wavelength, with an unknown wavelength stopping potential is 3 volt. It has been found that the unknown wavelength, when an unknown wavelength is made to incident on the same metallic surface, the stopping potential is found to be 3 volt. Then find the unknown wavelength. You have to calculate the unknown wavelength. Solution. We know that the maximum kinetic energy that is related with the stopping potential. So given parameters are, one is stopping potential, that is 3 volt. We have given the threshold wavelength, that is 5000 angstroms. Now we have to calculate the wavelength of the incident radiation. Let us suppose the wavelength of the incident radiation is lambda, and we have to calculate this. Now we will determine a relation in which the stopping potential, threshold wavelength, and the wavelength of the incident radiation are related to each other. We know that K max, because K max is related with this is always equal to h nu, energy of the incident photon, minus the work function. Minus the work function. Or K max is equal to E V naught, that is E into V naught. We know this. H is equal to H, this is energy, Hc by lambda, minus phi naught. This is Hc by lambda naught. Thus, this is a fundamental constant. This is the charge of the electron. This is known to you. These are fundamental constants. H and C, their product comes out to be, as I told you, 12,400 electron volt angstroms. We have to calculate the lambda, and this is also given. Now, substitute the corresponding values. You can write it as, now V naught. E into V naught is 3 volt is equal to Hc. This is 1 by lambda minus 1 by lambda naught into Hc, or this is equal to 3 electron volt is equal to 1 by lambda minus 1 by 5000 angstroms. Hc, it is 12400 electron volt angstroms. Now example third, a beam of light consists of 4 wavelengths, 4000 angstroms, 4800 angstroms, 6000 angstroms, and 7000 angstroms, each of intensity 1.5 into 10 to the power minus 3 watt per meter square. The beam falls normally on an area 10 to the power minus 4 meter square of a clean metallic surface of work function 1.9 electron volt. Assuming no loss of light energy, that is, each capable photon emits 1 electron. Calculate the number of photoelectrons liberated per second. Here in this numerical, we have been given 4 different wavelengths, 4 different photons, which are made to incident on a metallic surface whose work function is given, and the part of the area of the metallic surface, which is 10 to the power minus 4, that is also given. Now, we have to, it is also given that there is no loss of light energy. That means the number of photons which are made to incident on the metallic surface, all those capable photons whose energy is more than the work function of the metal, they are able to make the electrons to come out from the metallic surface. Thus, we can say the number of photons which are made to incident on the metallic surface, which are capable. All those electrons, all those photons which are made to incident on the given metallic surface in 1 second, they will be equal to the number of photoelectrons which are coming out from the metallic surface. Thus, we have to calculate those number of photoelectrons. So, here, first of all, let us see what are the parameters which are given. Solution. Lambda 1 is equal to 4000 angstroms. The energy of the photon of this is given by Hc by lambda 1, which is 12400 electron volt angstrom. divided by lambda 1 is 4000 angstroms. This is equal to 3.1 electron volt. Similarly, lambda 2, that is 4800 angstroms. So therefore, energy of the photon which corresponds to this wavelength is equal to hc by lambda 2, which is equal to 12400 4800 angstrom, electron volt angstrom, that is equal to 2.58 electron volt. 2.5 lambda 3, that is 6000 angstroms. So E3 hc by lambda 3, which is equal to 12400 electron volt angstrom divided by 6000 angstrom, which comes out to be 2.06 electron volt. And lambda 4, which is equal to 7000 angstroms, which is E4 is equal to hc by lambda 4, which is equal to 12400 electron volt divided by 7000 angstrom, which is equal to 1.77 electron volt. Thus, the energy of the photon, which corresponds to the wavelength lambda 1, it is 3.1 electron volt, which is greater than the work function. Which is greater than the work function. This is work function of the given metallic surface. So therefore, these photons are able to impart the appropriate amount of energy to the electrons in the given metallic surface, and hence these electrons will come out. So now we will calculate how many photons of this wavelength are made to incident on the metallic surface in 1 second. If we are able to calculate that number, same number of photons, because each photon, it is given that each capable photon emits 1 electron. So therefore, each photon of this energy is able to make the electron to come out from the given metallic surface. Similarly, lambda 2, in this case also, the energy is greater than the work function. Here work function is 1.9, it is 2.58. It is greater than the work function, therefore these photons are also able to impart the appropriate amount of energy, and hence electrons will come out from the metallic surface. Same is the case with lambda 3, but the lambda 4, the energy of the photons which corresponds to the wavelength having 7000 angstroms, the energy of these photons is less than the work function, that is 1.77 electron volt. This is the work function is 1.9 electron volts. Therefore, these photons are not able to interact with the electrons, and hence electrons will not come out by these photons because the energy is less than the work function. Only these three are capable. The photons of these three wavelengths are capable to make the electrons to come out from the given metallic surface. Now we will determine how many photons of these three wavelengths are made to incident on the given metallic surface in 1 second. Same number of electrons will come out from the given metallic surface. Also, it is given that the intensity of each, let us suppose the intensity of the light whose wavelength is lambda 1, let us suppose that is I1, that is equal to also I2, that is also equal to I3. The intensity of each radiation is same, and that is equal to some 1.5 into 10 raised power minus 3 watt per meter square. It is given, and area of the surface on which the light is made to incident, that is 10 raised power minus 4 meters square. We know that if n is the number of photoelectrons emitted from the metallic surface, if n is the total number of photoelectrons which are being emitted from the metallic surface, that n is equal to n1 plus n2 plus n3. This is the total number of photons which are made to incident per second. And because we know that, as I told you, the number of photons, the number of photoelectrons which are emitted from the metallic surface, that is equal to the number of photons which are made to incident on the given metallic surface per second. So therefore we can say number of photoelectrons emitted per second is equal to number of photons incident per second. Or we can write it as this is equal to N1 plus N2 plus N3. But we know that since the parameters which are given, that is the intensity, that is the area, and that is the energy of the photons. We know that the number of photoelectrons which are emitted from the metallic surface, that is equal to I1 A1 divided by E1. This is the relation, plus I2 A2 divided by E2 plus I3 A3 divided by E3. Since I1 intensity in each case is same and area is also same, so therefore we can write this is 1 by E1 plus 1 by E2 plus 1 by E3 I common. When we substitute the corresponding values of this quantity, the number of photoelectrons which are emitted per second, that comes out to be 1.12 into 10 raised power 12. The number of electrons which are coming out from the metallic surface, that means the number of photons which are incident on the given metallic surface, that is this much, which are capable, whose energy is more than the threshold energy, that is this much, and same number of photoelectrons will come out from the given metallic surface. Thank you.